Hello, I'm Doug, Stand-Up Physicist. Today I am going to discuss a personal issue I have with tensor calculus. Now it's personal because this issue is actually well understood, just not by me. And that happens from time to time. That, there's an issue that's taught in the beginnings of books on general relativity. And I know how to parrot the right answer. Teacher says this. Teacher says this. Teacher says that. Teacher says that. I suspect that there's some outstanding A+ students who are simply very good parrots. Now, I shouldn't knock parroting that much because I do it myself. But it's to really understand something, you have to understand it from a bunch of different angles. And that takes time and effort. And there's just so much to learn that it's often, really necessary to just learn how to parrot and figure out how everything interconnects later. Like, if you ever had to teach a subject, well, that's when you'll see how everything interconnects and gives you exactly the same answer no matter which direction you look at it from. Of course, I haven't taught tensor calculus, so this one little math thingy that I didn't get was because I didn't teach it. Actually, I have come to peace with it recently, and that's what I'm going to try and explain in this short half-hour video. So now I'm going to have to go into the background of this issue, because most of you don't even know what tensors are. Well, tensors are used everywhere, at least in physics. They're used to describe the standard model, which is how particles interact, and it is used in general relativity. And since those two laws govern all the four known forces of nature, you might say tensors are used to describe everything. Again, at least in physics. So what are these things? Well, what can you do with them, for example? Well, you can add them together. You can multiply them by a scalar. You can use whatever coordinate system you choose, and they will still hold up. You can work in arbitrary numbers of dimensions, and people who work with strings do such things, but I will stick to 4 dimensions. That is 3 for space and 1 for time, and never take a step beyond that. Now, tensors actually have a bad rep on the street. Why is that? Why are they considered scary? Well, they're scary because they use Greek letters. Not only that, some of them are up, and some of them are down, and it matters if they're up or they're down. So, we've got to learn those rules, okay? So the ones that are up, they're called contravariant vectors. They're up, they're positive, okay? The ones that are down, well, they're kind of negative. Kinda. Because the first term is actually positive and the next 3 are negative. So you must memorize those rules. Contravariant vectors are up and positive. Contravariant vectors are up and positive. Covariant vectors are low and the final 3 are negative. Covariant vectors are low and the final 3 are negative. A+, Mr. Parrot. But then you say, why? So I'm going to spend a little time explaining the why. It has to do with a collision between Pythagoras and Albert Einstein. Pythagoras has got 2,500 years of fame because he figured out that for a right-hand triangle, that this side squared plus that side squared equals the diagonal side squared. They still teach that today. It's still true today in a two-dimensional plane. In fact, it's even true in a three-dimensional plane. So x squared plus y squared plus z squared equals the distance between those 2 points. And like everyone else, Einstein learned Pythagoras' theorem when he was in school. But as a teenager, you know, I played pinball machines at an airport, but Einstein actually thought about what it would be like to sit on a photon and try and measure stuff. He was a hardcore physics guy, okay? And he had to think about that problem for like 10 years, all right? And at the end of all that thinking came a field of study known as special relativity. The physics of going wicked fast. And the thing is that if you go out on the internet, you'll find a lot of confused opinions about what's going on, about things contracting and clocks speeding up or slowing down or maybe doing both. And it's easy with the internet not to get a clear picture of what's going on. So I'm going to do a couple of things for the sake of clarity. One is I'm going to recommend a book. It is this one, Space-Time Physics by Taylor and Wheeler. All right. Wheeler was one of the top theoretical physicists of his day, and Edwin Taylor is an absolutely first-rate educator. And what they did was they were able to use high school level math and focus on what people can agree on more than what they differ on, because that gets hard, okay? So what do you and I agree on? What do we disagree on? Okay, let's make this real clear. Your clock always looks the same to you. Your ruler always looks the same to you. Same rule applies to me. My clock right here always looks great to me, and my ruler always looks great to me. Now, where it gets confusing is if I am moving fast relative to you, and I look at your clock, then when I look at your clock looks a little odd. When I look at your ruler looks a little odd. When you look at my watch, it looks a little weird. When you look at my ruler, you say, hey, something funky's going on here. So, the question becomes, what can we actually agree on? What we can actually agree on is Einstein's update of Pythagorean's 3D theorem. What Einstein basically said was throw in times squared and we're going to be able to find something that we agree on. Now you go, hold on a second. This measures in seconds. Everybody agrees on that. But the ruler thing, that's measured in meters. If you're in a sane country, unlike the United States where they use feet, maybe I shouldn't get into that. But anyway, that's a distance squared. Meter, not a second. Second, not a meter. I mean, that's true. Okay? You're right. So you can actually use the speed of light c, which is meters per second, to convert between the two. So if you take time in seconds, multiply that by c, meters per second, that ends up with meters. So c times time is meters, as is meters, meters, and meters. Okay? So what Einstein said everybody's going to agree on is that c squared t squared minus x squared minus y squared minus z squared That's called the Lorentz invariant interval. That everybody's going to agree on. And believe me, there are more than enough experiments have proven that is in fact the case. And that's a major theme in that space-time physics book, is that we're just taking that Pythagorean thing. Oh, you know those minus signs in there? That's where a lot of the confusion just happens to be from. But that's been confirmed by all kinds of experiments. And it confuses people to this day. And I think in 100 years, there'll still people say, oh, Einstein's wrong. It's like, no, they didn't get this update thingy, okay? And because it's hard to, it's actually hard to understand, all right? But that's all you got to know, so we can return to tensors, all right? Invariant means that it does not change. And that's the most important word in the Lorentz invariant interval. It doesn't change. Everybody agrees on it. Contrast that with the word covariant. What that means is that we know how something changes. And so to have a complete picture of what's going on, it's absolutely vital that you describe what is Lorentz invariant. In other words, everybody agrees to it, it doesn't change. And what is Lorentz covariant? Everybody knows that that changes, and they kind of even know how it changes. All right? Oh, but I just used the same word two different ways. That would be the word covariant. And I'm sorry, but physics sometimes does this. I mean, there's not a single letter that's different between the two, and yet they really do mean kind of different things. If I am talking about the Greek letters being up versus being down, the down guy, that's a covariant tensor. If I am talking about how things transform, if they don't change at all, they're invariant, but if they do change in ways that we understand, that is covariant. I'm sorry, but you're just going to have to read into the context of the discussion in order to figure out which one I was actually using. Now we can go back to tensors. So what we're going to do is we're going to take a contravariant vector and contract it with a covariant vector. Okay? So let's do this. The contras, they're all positive. This one positive first and the other three negative. So CT times positive CT, that is C squared T squared. Then plus X minus X squared plus Y minus Y squared plus Z minus Z squared. So the sum of that is C squared T squared minus X squared minus Y squared minus Z squared. It's like, oh, that's the Lorentz invariant interval. So this whole game of upper versus lower was designed so that when you contract an upper with a lower, you get a Lorentz invariant. It was all designed to do that. Now, I'm actually at peace with that, but for a rather unusual or unique reason. And that is because I happen to be an expert in something called quaternions. These are numbers with 4 parts, and they're numbers in the usual sense of the word. You can add them, you can subtract them, you can multiply one by the other, you can divide them one by another. And in that sense, I think of them as an upgrade to tensors. Now granted, they're stuck in 4D, which is fine because I'm stuck in 4D. Why shouldn't my math tools be stuck here with me? But it means that not only can I add and subtract and multiply by a scalar like I can with tensors, but I can multiply one by another. I can divide by them. And that seems to me to be worth the hassle of using them. Now, I should say that they don't usually teach this at the college level. They usually don't get into it except as, you know, oh, there's these little things as this little side dish for graduate level studies, even in theoretical physics. And maybe the theme you should kind of watch during the show is just like how using quaternions does a lot of things like really in a natural way. And maybe there's kind of a message in there. We'll see. So the rules are pretty easy to find on the internet. You go to quaternions.com. I own it. The Wikipedia will show you how to multiply these two things together. But let's do so right here. If you take that 4-vector before, which, as I say, you can upgrade to the Quaternion level, and you just say, let's form the Quaternion product, just tell me, what is the answer? And the answer, if I just take CT, X, Y, Z, and square it, is that the first term is C squared, T squared, minus X squared, minus Y squared, minus Z squared. And there are 3 other terms. There's 2 CTX, 2 CTY, 2 CTZ. So that would mean that the first term is the Lorentz invariant interval, and the final 3 are Lorentz covariant. We understand how they change under a Lorentz transformation. Now, there are 2 really remarkable things about that. First of all, I got the Lorentz invariant interval without needing any Greek letters, without having to write something was covariant or contravariant, okay? It just showed up. And that was actually the entire observation that got me involved with quaternions. I said, that's not lucky, that's telling me something. And, you know, a few months later, I went out and bought the domain name. I thought it was that important because I'd spent that much quality time with Space-Time Physics by Taylor and Wheeler to know that the interval, the Lorentz invariant interval, is just at the core of special relativity. And so if this just shows up by accident, that accident is trying to tell us something, okay? So that was totally cool. No Greek letters, I just got it in the bag, right? And but how about these other 3? Well, this is actually remarkable to me because, as I say, that interval is super important, and these other 3, they don't even have like a name, okay? You know, you take one distance times another distance, we call that an area, okay? Take one distance, multiply it by a time, and you got a, I don't know, okay? But they're like next door neighbors to something that's centrally important to standard modern physics, you know, special relativity. I'm really you know, scratching my head about that. So I am like completely comfortable with what is widely known, okay? It is just widely known and accepted that if you take a contravariant vector and you construct it with a covariant vector, you get this Lorentz invariant interval. And the reason is because I come at it from the Quaternion angle and I just say, square the suckers, look at that first term, and bingo. You've got exactly the same thing, 2 different ways. I feel rock solid. So now we're in a position to finally get at my personal issue, okay? So the personal issue has to do with taking derivatives, okay? There are contravariant derivatives. There are covariant derivatives. There are those that have the terms go positive, all positive. There are those that have the terms go all negative. You know, it's as you'd expect, except it's not. In that the contravariant vector, that's all positive, but the contravariant derivative has a positive time derivative and a minus divergence. And the covariant vector, that's the guy that threw in the minus, the covariant derivative, it has all positive. So I think I resisted this because it took me a while to memorize that other rule. And I was just pissed that they were like changing their mood like immediately, you know? Oh, believe me, they weren't that flip, okay? They talked about it being a dual space, you know, and I, of course, cheated a little bit and thought about, you know, derivatives being like dividing by that differential, which you're not supposed to do, and maybe that makes it a dual space. I know that you're not supposed to, but that kind of made me at peace. And believe me, they actually go through this kind of algebraic argument that just says, you know, for sure, that's the way it's got to be. For some odd reason, I never wrapped my head around that. It's the kind of thing that, you know, if I devoted considerably more time, I might have got it. I mean, I did learn to parrot it, you know, that a contravariant derivative has a positive time derivative and negative for the space ones. A contravariant derivative has a positive time derivative and negative for the space derivatives. And a covariant derivative is all positive. A covariant derivative is all positive. But I wasn't a happy parrot. So then it says, well, how can I make my parrot happy? And so I started to think about it in terms of quaternions. And I actually had this for like years, maybe even as long as a decade, but I didn't try and map it to the tensor terminology until recently. And so that's what I'm going to do for you here, all right? So how do you do this with quaternions? Well, take a 4 derivative and upgrade that to a quaternion. And take a 4 potential, upgrade that to a quaternion, multiply the two together. What do you get? Well, you get d phi dt minus the divergence of A. Then you get the time derivative of A plus the gradient of phi plus the curl of B. All right? Now that was just a math exercise. But what's totally remarkable, if you know a little about electromagnetism, is that the 3-vector part is also a way to write the B field minus the E field. I mean, that's physically relevant. And all I was doing was trying to multiply these two together, and I have a connection to physics. I was like, wow, that was really, really cool. But what about that scalar in there? I have d phi dt minus the divergence of A. Well, how do I deal with that? So what would tensors say? And so let's take a covariant derivative, because that one's all positive, and contract that with the contravariant potential. That's all positive. I bet the result is going to be all positive, but it's also going to be Lorentz invariant, because that's what happens when you do one of these contractions. So a Lorentz invariant quantity will be d phi dt plus the divergence of A. Okay, well that's good. And when I did this quaternion multiplication, I got d phi dt minus the divergence of A. And I said, what does that mean? And when you're confused by this, but you have a life, then it's time to walk the dog. So that's what I did. I did that calculation in the morning, and I said, but it's time to walk the dog. And so I walked the dog and let the dog do the dog thing, and, you know, collected the thing in the bag and disposed of it, and kept on thinking about this difference in sign and said, is this good? And by the time I got back, I said, this isn't good. This is perfect. Absolutely perfect. The reason that it's perfect is that if you think of that 3-vector when I did the quaternion thing, what you say in tensor lingo is that transforms like a rank 2 tensor. Which means the vector, the differential part has its own boosty thing, the potential part has its own boosty thing. You had to take those two together And together that tells you how the whole darn thing will behave. It is covariant in the sense that we understand how it changes. It's really confusing, okay? You got to go back to Feynman book 2 and go through that chapter real slowly. But that's all he does. Does a boost to the derivative thingies, does a boost to the potential thingies, and says those two get together and whammo, yeah, you get, this is what you'll see. And it is what is seen, okay? It's spot on, it's right, okay? But what about that gauge term? Well, it's not Lorentz invariant. In other words, it doesn't have the plus sign. Well, that's excellent. That's what it's got to be. This thing has to transform like part of a rank 2 tensor like the rest of the terms. And when I thought about it, it's like if you take the covariant derivative of a covariant vector, or for that matter, the contravariant derivative of a contravariant vector, you're going to get exactly the same thing that I got with quaternions. That's going to be the terms down the diagonal of a rank 2 tensor. So it's going to transform like part of a rank 2 tensor. That is what it needs to be consistent, to make sense. And the reason this was so remarkable, for me anyway, is because here I've got these rules for dealing with tensors, with the up and the down and the flipping of the roles when you're dealing with derivatives. And it looks like they're all designed so that when you do the most simple and natural thing with quaternions, quaternions just work. That's stunning, okay? All right, so what do people actually do if they take a derivative and they act on it on a potential? I mean, how do they actually use that? Well, amazingly enough, those people who are really good with tensors, they actually take a contravariant derivative of a contravariant potential, and they contract that with a covariant derivative of a covariant for a potential, and they form a scalar out of that that is guaranteed Lorentz invariant. And I've actually done that exercise. And it's confusing because you got to keep track of which ones are positive, which ones are negative, which ones get together, okay? And then you got to smush them together. And it's a tough exercise. It's a good exercise, makes a robust mind, or strains old farts like myself. But I got it. And the result can be summarized very succinctly. It is the magnetic field B squared minus the electric field squared. It's like, wow, okay. Now, how do you do that with quaternions? Okay, well, if you take the derivative of a potential, there's something in that's kind of got a certain handedness to it. It's called the curl. So the opposite thing would be to write the potential and then the derivative, okay? And that would give you everything the same except the thing that has the curl, okay? Now, I should say another technical thing is when you're doing this particular exercise, you got to get rid of that scalar, and that's not too difficult, okay? So get rid of that scalar that I've just been discussing, okay, for these two. Then, as I already said, this is actually the B field minus the E field. And over here, the only thing that flips sign is the B field, so this is minus the B field minus the E field, okay? Now, since these are quaternions, I can just multiply these guys together. And what's the result? Well, the result is B squared minus E squared as the first term. That's pretty remarkable. But the other term is E cross B. And the reason that's amazing is because that's also physically relevant. It's called the Poynting vector, and it's a measure of the electromagnetic field energy density. I'm getting both of these for free. I mean, that's pretty deep stuff. So if you read on in these books, they say, well, not only is b squared minus e squared Lorentz invariant, but also b dot e. So then I said, well, I could do the tensor calculation, maybe, but let's just do it with quaternions. I wonder what that'll be. And what it turns out to be is you take this orientation, square it. Take that orientation, square it. And subtract the two. And what you get is actually only b dot e. The 3 vector is actually 0, 0, 0. So that was kind of cool. And I was going to actually leave it at that. I mean, my first draft of this talk, I was kind of there. It's like, isn't that amusing? I can get these both. And the more I thought about it, it's like, no, this is actually kind of might be deep, okay? I mean, if you're thinking about Lorentz invariant quantities, you know, things everybody can agree on, people aren't all going to agree on left and right. You know, they're going to say, no, I looked at it in the mirror and it was a different answer. So you kind of have to figure out how to, if you're constructing Lorentz invariants, how to box that out, okay? How to block it out. And so, first of all, you got to form both ways, okay? And one way, you just, you know, bang them together and you're kind of, and you get that b squared minus c squared. And the other way, you just square one, square the other, and boom, you got that. And so that was cool because I'd never seen anybody really go beyond the observation that these are Lorentz invariants, okay, these two. So now you say, but why does anybody care about these two Lorentz invariant intervals? And I've actually seen one of them discussed many times, and that is the b squared minus e squared. If you take that Lorentz invariant and drop it into the Euler-Lagrange equation and crank it on through, you end up with the Maxwell source equations. That would be Gauss's law and Ampere's law. And those are hugely important, okay? So, in fact, it looks like it's really scary. And in fact, I have another video where I go through it. And there's a lot of detail in there, and that's what scares people away. But if you know that x squared, what the derivative of x squared is, it's just 2x, and with respect to x. And if you know the derivative of xy with respect to x, well, that's just y. If you know that much calculus, and you can keep track of a whole bunch of different things, then you can derive the Maxwell equations, specifically the Ampere's law and Gauss's law. And that's a really wonderful thing. I highly recommend it for anybody who's a nerd. You know, that's how you prove it. You know, you have your 8.5 by 11 that's got it, and you say, yes, I know. So I've done that calculation. I've read many places where people say this is all that's going on, you know, and I was left wondering, you know, well, what about b dot e? I mean, shouldn't it? And I remember going, you know, it'd be really nice if, you know, b dot e, if you just put it in Euler-Lagrange and it got the other two. I mean, wouldn't that feel like complete, you know? So I didn't read this, okay? I just did the calculation. And lo and behold, that's what happens. If you take b dot e and you drop it into Euler-Lagrange, then you actually get 0, 0, 0, 0, all zeros. And if you look at it closely, you go, oh, there's the no monopoles law. Oh, there's Faraday's law, okay? But it's coming out of, you know, the way it should come out of. You should say, this is my action. This is my Lorentz invariant, and then I vary it with respect to the potential, and blammo, I've got it, okay? So I want you to just kind of take the big take-home picture out of here, all right? And that is that, sure, you can follow the usual education path and learn all these rules about tensors being up and down and the flip that happens because of derivatives. There's nothing wrong with that. Okay, it's worked for thousands and thousands of graduate students now. It will for them in the future, okay? But you can get another angle on it if you make an investment in quaternions. And the payoff to me is ridiculous, okay? Because all I'm doing is doing like the simplest darn things I could with quaternions. And I get Lorentz invariant intervals if I just square two things. If I have a quaternion differential acting on a quaternion potential, I get something that transforms like a rank 2 tensor. And then I got two choices to deal with that cross product-y thing. If I flip the order and I just smash them together, I'm going to end up with the first term going into Euler-Lagrange, and I'll be able to derive the Maxwell equations, specifically Gauss's law and Ampere's law. And then if I go, no, let's square one of these and then subtract the square of the other dude, then I go through the same machinery and I end up at the homogeneous equations, which would be no monopoles and Faraday's law. And I don't know, but I'm thinking this investment's paying off because I can spot with confidence how to derive the Maxwell equations, which are the most important, best understood field equations in all of physics. So I think the investment in learning about quaternions is well worth it. All right, thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah, math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof rocks.
That video had an awful lot of math. Okay, so I don't know if you noticed, but this is my pet sperm. And he really likes to meet people. Well, actually, only fertile women, but that's his own hang-up. And I was really realizing, actually, there's so many neat things about sperm. For example, I really shouldn't call it a him, right? Because half my sperm are female, okay? And this guy, he came in this great box here. My pet sperm. Okay, from www.mypetsperm.com. This is the pet with a purpose in life. Safe sex mascot. Good luck fertility charm. Widespread awareness products hopes to bring consciousness to all sexual decisions. Rock on. I think that's a great goal, and I do encourage them to on their project, their education project. But we're kind of physics nerds here, so let's think about some numbers associated with sperm. So I happen to produce 250 million sperm every single night. And I think most of those go to waste. I think that's bad. I was like, what would it take to get some use out of them? So there are about 300 million Americans, half of them being female. They're not all in the fertile range. Okay, so let's just guesstimate 100 million fertile females. And I thought, you know, it would take a lot of work just to contact those women about how I don't want to waste my sperm. You know, it would cost $44 million just to send them a little note explaining about my project. And that doesn't even cost, take into account the cost of the printing and the paper. I mean, I have a laser printer here, but I probably would have to replace the toner, you know? So I don't think I can really do that project. But I have been in a relationship with a lovely lady for now going on 15 years. And in that period of time, how many sperm have I produced? Well, I make 1 billion sperm in about 4 days. And so that means I probably make about 100 billion sperm in a year, or 1.5 trillion sperm over that time. And I could bring the subject up and see if she'd be willing to utilize every sperm I've produced. But that even runs into problems, because this pregnancy thing generally takes about 9.5 months, and you got to give her some time off, you know. So let's just say once a year she takes one sperm and has a new child. That would actually take 1.5 trillion years to actually use all those sperm. And the reason that's a problem is because the known universe is only 13 billion years. So she would have to last like 100 times longer than the known universe. Now, I know that, no, I don't know. I think she's going to last longer than I am, because I've got diabetes, celiac disease, a little heart valve problem. But I just don't think she's going to last that long. So I don't think that's practical either. But what has occurred is that exactly one of my sperm, in fact, it was a girl sperm to be honest, has actually produced a child, and she is an absolutely lovely lady, and I really enjoy all my time I spend with her. And so, you know, the numbers have worked out in my favor. Thank you very much.